Detect and freeze regression drift with a golden dataset. By the end, you will have a tiny, reproducible pipeline that maps text to numeric scores, measures how far predictions stray from a trusted golden dataset, and freezes expected outputs to flag drift. You will also learn a simple calibration trick to tighten the fit. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. Real teams use golden datasets to lock in expected behavior. You pick a small, trusted set of inputs and known outputs. Then you check future model runs against that ground truth. Success looks like stable scores and quick alerts when a change makes the model behave differently. The downside is this only tests a slice of behavior. It is a focused safety net, not a full test suite, but it catches obvious regressions fast. At an intuitive level, think of a golden dataset as a reference list of examples you care about. Each example has a canonical score. You run your model, compare its scores to the canonical ones, and measure error. If error grows after a change, you want a clear alert. This approach is simple and practical. It works well for small teams and for critical behaviors that must not drift. We will build a compact pipeline that maps text to scores, computes error on a golden set, ranks the worst cases, applies a linear calibration, and finally freezes outputs to detect drift. First, we create a deterministic scoring stub to simulate a model output. This snippet builds a deterministic stub that maps text to numeric scores. It creates a predictable function that turns each string into a numeric value, so you always get the same output for the same input. Use this when you want to test the rest of the pipeline before plugging in a large model. If you increase the complexity of the stub, the tests will better mimic a real model, but they will take longer to run. Keep the stub simple for fast iteration and swap in the real scorer later when the rest of the pipeline looks right. Next, we measure how much the stub differs from the golden answers. This example evaluates predictions against a tiny golden dataset using MAE, which is mean absolute error, and computes the average absolute difference between predicted and expected scores. It iterates over the golden examples, collects predicted values, and returns the average absolute gap. MAE is easy to interpret. Lower is better, and it penalizes all deviations equally. If you change the size of the golden dataset, the stability of MAE will change too. A larger golden set gives a smoother estimate, while a smaller one will be noisier but faster to run. Now we surface the worst mismatches so you can inspect failures. This code ranks cases by error to spotlight where the model struggles most. It computes absolute error per example and sorts examples from largest to smallest error. That lets you read the top offenders and see whether errors come from a few edge cases or many modest misses. If you limit the number of flagged examples, you'll get a focused debugging list. If you expand the limit, you get broader coverage but more to inspect. Use the ranked list to decide whether to update training data, adjust pre-processing, or refine expectations. Next, we apply a simple linear adjustment to tighten predicted scores. This snippet applies a linear calibration to improve the regression fit. It fits a slope and intercept to map raw predictions closer to golden scores, and then applies that affine transform to new predictions. Calibration often reduces systematic bias where predictions are consistently too high or too low. If you allow more flexible transforms, you might reduce error further, but you also risk overfitting the small golden set. A single slope and intercept is a conservative choice that often yields measurable improvement with minimal risk. Finally, we freeze expected outputs and check for drift after a change. This snippet freezes expected outputs and flags behavior drift after a change. It records the calibrated predictions for the golden set and then compares new runs to that frozen baseline. If the differences exceed a threshold, the pipeline raises a warning or fails a test. Freezing gives a stable regression gate so that any code, dependency, or model update that alters these key outputs gets noticed. If you tighten the threshold, you get fewer false negatives, but more false positives. If you loosen it, you might miss subtle regressions. Recap: a golden dataset is a small, trusted sample of inputs with known outputs. Use it when you need a fast regression check for critical behaviors. One caveat: it does not replace broad evaluation. It tests only the frozen slice you choose. For the next step, extend this exact approach by scaling the golden set and adding timing and accuracy checks, so you measure both correctness and latency under the same freeze policy. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.